All right, so this is our Deep Thought podcast, and my name is Brandon McCoy, and this is Jordan. And today we're going to be talking about how chaos emerges as a byproduct of increasing technological advancement. So, just to start into that, I'm going to ask Jordan here what chaos is. What is chaos?
Basically, chaos is, I haven't thought of this yet, but it's not, I think I would describe it as like it's just the unpredictability of sort of like systems that have like moving parts maybe, or things that are just kind of like dynamic, and you can't really predict in the long term where it's going until you actually observe it. Then you're not really predicting. So basically chaos is just, it's chaos as you pretty much think of it. Like so it's unpredictability of the future.
Yeah, stuff you can't determine.
Yeah,
what's
non-deterministic.
Gonna happen, how it's going to happen.
It's synonymous to say non-deterministic and chaos. They're pretty much the same thing. So if you're familiar with that, then that's, yeah.
Right, so then in the real world, there's 3 examples that you came up with of real world chaos, and what are those?
So they're in the real world. Okay, so physics. We see it everywhere, and so like from driving cars to satellites in space to like throwing a baseball, whatever there's physics everywhere, obviously. So and this is chaotic. I was gonna say because when you have a lot of moving bodies, such as planets in space, this is a good example, chaos emerges from this because they have these simple rules that govern their behavior, but in the long term, we can't really tell what they're going to do until we just kind of like simulate it or observe it. So I mean, I guess planets in space are maybe not the best example, because they have this orbit around a star and all that stuff, and we can predict that in the long term. But it's things like, say, if there are 2 colliding galaxies, that's a much more chaotic system, just because you have all these large bodies, such as planets and stars, and maybe bigger things like black holes, moving around, and then you can't really tell what's happening there, until you just observe it. You can't tell what the result is going to be, other than just some kind of mess. So that's chaos, right? So physics is one good example of that, and that's specifically astrophysics. But you can apply it to normal scale physics that we're used to, and even probably atomic physics as well. I'm guessing. Don't really know on that one. And then also. A second example of chaos is biology. So when we have these organisms that are reproducing and proliferating, right? You can't really tell where it's going, other than, you can model its population growth, but you can't really tell what like their actions are going to be. So that gets philosophical and maybe religious, if you want to say if they've got like free will or whatever, but at the end of the day, we know that actions are mainly driven by needs, right? So that's the biology there. So the chaos emerges from that because there's simple rules of like, I'm hungry, I'm gonna go eat. So that kind of thing, right? So then there's that action that takes place, and that affects the system chaotically. So that's another example of chaos. And then the third example that I like to think about in the real world is space and time. So it's a little harder to relate this to chaos because it's specifically the infinite scale of time and space. So time can be divided infinitely, theoretically. There is the Planck time and the Planck length for space, which is kind of a way to discretize our world, but the idea of it is we have this infinite scale, pretty much. So time goes on forever, and you can scale up forever, and you can divide it pretty much infinitely as into as small chunks as you want, and the same goes for space. As far as we know, I mean, we have the observable universe that's finite, but most people believe that there's more beyond the observable universe, so that's pretty much going to be infinite, probably. It's not like there's going to be some wall we hit.
Could you say that the more moving parts a system has, the more chaotic that it is? Because if you think about space in terms of how many moving parts it has, like the universe and galaxy has so many different moving parts, that makes it more chaotic, or does it matter?
As soon as you have 3 atoms, there's chaos. 2 atoms, there's no chaos because there's gravity between the two. More like if there's matter that does not interact with each other. I mean, if you have 2 gas particles that don't interact, then yeah, that's enough for there to be stability in some kind of system. But if there's a 3rd atom, and obviously there's more than 3 atoms in the universe, but as soon as there's a 3rd atom, they call it the 3-body problem. That's very related to the TV series. If you've seen that, you're probably familiar with that. And so the 3rd body, as soon as you add that 3rd body, that dynamical system, which we would model with math and all that stuff, is now chaotic under most conditions. Now you could set it up in just the right way so that it's deterministic if you have perfect starting conditions for it to have a stable point, or an equilibrium, I mean. But if you adjust it just a tiny bit, that's called a perturbation. So it's perturbed, and that tiny adjustment causes the long-term behavior to be drastically different, and that's a property of chaos. So you got these 3 particles. They could be 3 planets or 3 stars, 3 anything with gravity, and they would be circling around. But then not just circling around. Sometimes they'll just randomly fly off and come back, and then be stable again or fly off again. So that's why it's chaotic, because you wouldn't really know what's coming next.
Right. Okay, so in the real world, we've got physics, biology, and the large scale of space and time. Those are our 3 main chaotic things. What in the conceptual world is a definition of chaos? How do you define chaos in terms of math and theory?
So how do we use math to define
Well,
that stuff? Sorry.
You had 3 conceptualized versions of the 3 real world versions.
Oh yeah, the parallels. I'm sorry. Yeah, of course. Yeah.
I guess how did they relate back to the real world?
Yeah. So, I think it's a fascinating idea to form this connection between physics and dynamical systems. So dynamical systems is just the math, really. But physics is the strongest sort of application of dynamical systems. And then biology is very strongly related to cellular automata. And that's a whole other thing we could talk about. But and basically with cellular automata, you just got these individual sort of pieces kind of interacting with each other, sort of based on their surrounding environment, right? So as you could tell, based on that simple description of cellular automata, that's very similar to biology in real life. So there's that connection to be made there. And then there's, with space and time, both being infinite in scale and all that stuff, you can draw a connection between that and fractals in math. Fractals are purely mathematical, but we can see a resemblance of fractals in space and time. So, and all of these 6 things, these 6 things I've mentioned now are all chaotic systems. It's chaotic in nature, intrinsically chaotic.
So then real quick, what's a definition of dynamic systems, cellular automata, and fractals? How would you define each one of those in a couple sentences?
Yeah, so a couple sentences, I'll try my best.
Or is it just like a quick little one sentence thing? Like dynamic systems is just like physics, right?
Dynamical systems are systems of equations. They're systems of differential equations or difference equations. One is discrete, so I don't mean to describe too much. I'm trying to keep this concise. Dynamical systems, basically they are equations that represent quantities that change over time. And these quantities could be positions of objects, they could be energy amounts in matter. So you can see how that ties very closely to physics. And then also cellular automata, I kind of already gave a brief description of that. It's like these little
simulations?
It's like well, I mean, we would simulate it. That's how we simulate. We don't actually see cellular automata in real life, other than the closest resemblance of it is biology. Cellular automata are basically like the most famous example of that is Conway's Game of Life. You can look that up and see how that kind of looks, and that's basically the basis of all cellular automata, but make some variations here and there to make your own cellular automata. But there's a more rigorous definition of that if you wanted to look that up. And then fractals. Those are, there's definitely a very mathematical description of it, or definition, but I like to think of it as they're shapes with infinitely complex contours. So 2D, it could be 3D, it doesn't really matter, but if it's a shape with some kind of infinitely defined contour, or shape, I guess you would call it.
And you can look up images of them. They're like the infinitely growing geometric shape. It just repeats itself over and over again. It gets tinier and tinier as it goes out.
Sierpinski triangle, Mandelbrot fractal, Julia fractal, those are all good examples of looking at fractals.
So I guess to wrap this up, how does chaos affect human beings, and how does it play into our life?
Right, so this is very interesting. So the very specific example of where we can see this happening with our day-to-day lives, specifically now in this time of history, is cellular automata. So when you see this, I mean, really, actually, any chaotic system will kind of behave like this. So the property of chaos is that if you start with some initial conditions, like the three-body problem, you got the 3 planets or whatever, they start with immediately calculable, whatever the word is, futures. And so very quickly, it'll devolve into chaos. And you can kind of think of how that starts, there's order. It starts with there being some determinism there, but then you start to not really be able to see anything, and it's unpredictable after that. So we can relate that to our technological advancements in recent history. So we have we started thousands of years ago with counting, and then we invented algebra, and then 1,000 years after that we invented calculus. 200 years we got an industrial revolution and electricity and stuff like that, and then 100 something years we had computers, and then 50-ish years we have AI, and then it seems like in 20 years or whatever there's going to be another invention that drastically changes the world like the previous ones did. And that's chaotic sort of behavior for that to be like that.
Because all these different new technologies are popping up.
Yeah.
One right after another, even more quickly than they used to. It's just a snowball effect, right? Is how you want to.
Yeah, snowball effect. It's like it's exploding. In fact, of course, they call it the intelligence explosion. So, yeah.
Right.
Yeah. So it's chaos.
But then, in an explosion of intelligence, that kind of makes everything a little more confusing and chaotic, which is a weird irony of it. If things are more chaotic,
then you're less intelligent. Yeah, because you don't know what's going on.
Right. Yeah.
So.
Too much data. Okay, so in summary, we talked about how chaos emerges from this increasing technology and how chaos can be grouped physically into physics, biology, and the large scale of time and space, the infinite scale of time and space, and how that relates to conceptual constructs of dynamical systems, cellular automata, and fractals. And there's lots of parallels between those 3 things in each category. So,
yeah.
Anywho, that's the Deep Thought Podcast.